That covariance is called gamma k. The autocorrelation at lag k is gamma k divided by gamma 0. It standardizes linear dependence to lie between -1 and 1. Weak stationarity is the working framework for many linear models, but it does not by itself guarantee a law of large numbers or a central limit theorem. Additional moment and dependence conditions are needed. Strict stationarity does not imply weak stationarity unless the required moments exist. An independent sequence with a common Cauchy distribution is strictly stationary because its joint distributions do not depend on time, yet the Cauchy mean and variance are undefined, so the process cannot satisfy the finite moment conditions of weak stationarity. Weak stationarity need not imply strict stationarity. Imagine independent observations that alternate between a standard normal distribution and a centered uniform distribution with the same variance. The mean, variance, and every non-zero lag covariance stay constant. The marginal distribution nevertheless changes between odd and even dates, so strict stationarity fails. Heavy tails make moment assumptions substantive. A student t distribution with at most 1 degree of freedom lacks a finite mean, and with at most 2 degrees of freedom lacks a finite variance. Pareto and stable distributions can have similar problems. We must check moments rather than infer them from a familiar distribution name or from a finite plot. Time series models are often built from innovations. Independent and identically distributed innovations have a common distribution and are mutually independent, usually with mean 0 and constant variance. This strong benchmark makes calculations easy, but financial shocks can be unpredictable in their mean while still having time-varying conditional variance. A martingale difference sequence, or MDS, requires the conditional expected innovation given all past information to be 0. It rules out predictable conditional means, but permits changing conditional variance. This distinction becomes central in volatility models. An innovation can surprise us in direction, while the likely size of that surprise remains forecastable. White noise has mean 0 constant finite variance and 0 covariance at every non-zero lag. It need not be independent. A 0 mean independent and identically distributed sequence is an MDS and white noise. An MDS with constant unconditional variance is weak white noise. The reverse implications generally fail, so the label white noise should not be read as independence. Ergodicity matters because econometricians usually observe one economy or one market through time, not thousands of independent copies at the same date. An ensemble average uses many independent realizations at a fixed time. A time average uses many dates from one realization. Ergodicity connects the second object which we observe to the first object which defines the population. Stationarity alone does not create that connection. Let one random variable z be drawn once and set y at every date equal to z. The process is strictly and weakly stationary. Its time average always equals the same draw z, however, and does not converge to the population mean of 0. The process never forgets its initial random component. For a covariant stationary process, the variance of the sample mean reflects all autocovariances. Each lag receives a weight determined by how many observation pairs are separated by that lag. If dependence decays slowly, many observations carry overlapping information, and the sample mean can remain noisy, even in a long sample. A sufficient condition for mean ergodicity is absolute summability of the autocovariances, or equivalently of the autocorrelations after scaling. In words, the total absolute dependence across all lags must be finite. Then the variance of the sample mean tends to 0, and the sample mean converges in probability to the population mean. A random walk gives the contrasting case. I at time t equals y at time t, minus 1 plus a new innovation. Its variance grows linearly with t, so it is not covariance stationary. Shocks have permanent effects. Paths drift apart, and a sample average does not stabilize around one fixed population mean in the usual stationary way.